Hi, I'm Max.
I'm Chris.
And I'm Charlie.
And we're here today to talk about moment of inertia.
Moment of inertia is basically an object's resistance of change in motion.
And today you're going to learn about what torque is, what the moment of inertia is, and why exactly this wheel is doing this weird thing.
So we already know the force equals mass times acceleration equation. But how would we relate this to a circular object? Well, there's an equation for that as well, which is torque, which is related to the force, is equal to the moment of inertia, which is I, and then the angular acceleration, which is alpha. And the I is equivalent to the mass, and the acceleration is equivalent to the angular acceleration from the force equals mass times acceleration equation. But how do we find I? Well, I is equal to the summation of the mass of a point on r squared, which is the radius. And if we look at the object, let's say it's a circle, and there's an axis of rotation right in the center, and then there's a point somewhere on that circle. The m is equivalent to that point, and then the r squared is the radius from the center of the circle. But it doesn't have to be a circle, and the axis doesn't have to be in the center. It can be any strange shape, and you could have the axis on the left there, and the r is still to that point, and then the m is still the mass of that point. So it doesn't have to be a circle, and you can still find the moment of inertia.
Alright, so torque is basically force applied around an axis of rotation on an object. You can see here in our first equation that torque equals the force across the radius at which the force is applied on an object. You can see that with this wheel, when I apply a small force here, it doesn't move very fast. But when I apply a larger force there, it moves much faster. The same thing goes for the radius, where if I take the half of the radius here and apply a small force there, it doesn't move very fast. But if I apply the same force here, it moves faster. Our second equation shows the relationship between torque and moment of inertia and angular acceleration. Angular acceleration and moment of inertia are inverse related when it comes to a constant torque. So if angular acceleration is increasing, then moment of inertia has to decrease if torque remains constant. Same thing goes the other way around.
So, we've learned that the moment of inertia of an object is dependent on its distribution of mass, and common moments of inertia can be found for common objects. These are three pretty common objects, a sphere, a cylinder, and a hoop, which have these moments of inertia, which can be calculated with some pretty scary math. So, let's see how these apply in the real world.
They see me rolling, they hating, patrolling and trying to catch me riding dirty, 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 trying to catch me riding dirty. My music's so loud, I'm swinging, they hoping that they gon' catch me riding dirty.
So how did the race turn out the way it did? Well, looking at both the equations that we derived and the graph that compares the moment of inertia and the angular acceleration, we can see that the sphere has the lowest moment of inertia, and going on this, it's going to have the highest acceleration, with cylinder being second at half. So again, it's going to be still going up here. And then finally, mr squared is going to be the biggest one, so even farther down with the lower angular acceleration.
Alright, so we promised to explain what was going on with that weird tire, right? And here's the explanation as briefly as we can give it. There is a quantity called angular momentum, denoted by this L, which is similar to normal momentum, which is mv, in that angular momentum is I omega, where omega is just the rotational velocity. Now, you'll note that angular momentum is a vector quantity, which means that it has direction. So to change the direction of the angular momentum of, say, a spinning tire means to turn it while it's spinning. But this requires energy or force because it's momentum and it wants to be conserved. And that's why a tire is going to try to stay upright, which gives it that very bizarre effect of staying upright against gravity.